Welcome to another topic, that is normal force for an object on a horizontal surface. In this session, we are going to analyze with respect to the normal force for the object, how it relates to the action and reaction pair for the gravitational forces. What are the action and reaction pair for the normal forces? Also, with respect to understanding the normal force, we will be covering the conditions which are required for the normal force to exist. Also, why do we have the normal force in the first place? What is the reason for it to be present? In what scenarios the normal force will be applicable? So, scenarios of the object at rest or in motion along the surface. We will also talk about the direction of the normal force, yeah, because it's a force and a force will have a magnitude and the direction. And finally, there will be some viewpoints presented. So let's start. So let's take the case of a block on a horizontal surface. So we have a system which is made up of two objects over here. We have a block which is having a mass of m kg and it is at rest on the ground. Alternatively, I'll be calling it as Earth, keeping in view the nature of the forces that we are going to discuss. So first question, what are all the forces acting in this system? So system is made up of block and the ground or earth. So what are all the forces that come into play between these two objects? Yeah. So first set of forces will be the forces due to gravitation. So I'm going to explain it a bit more. So forces due to gravitation. Okay. And the next set of forces will be the normal forces. So what does each of them mean and what are the pairs that they make? We are going to discuss now more in detail. So each of them I have mentioned is a pair of forces. Now let's go into what is that pair? How does it look like? So before I proceed for the gravitational forces, I want you to be very careful with the nomenclature that I'm going to use. I will be representing a force with the letters like this, Fxy, which is the first letter X will represent, that will be the force by the object, could be one or two. And the second letter Y will represent the object on which the force is acting, object one or two. Yeah, so the objects will keep changing. It could be block, it could be earth. So let's see, what are the action and reaction force pairs as far as gravitational force is concerned. So we know that earth will exert a force of attraction. We know that earth will pull the object, the block in this case, with a force FEB. So that will be the force exerted by the earth on the block. And that is, we know that it's the weight of the object. So that will be equal to mg, the mass times acceleration due to gravity. So we know that action and reaction forces occur always in pair. We can never have any isolated force by its own. It's always in pair. So if I consider this as one of the forces in that pair, what's the other force? So the other force due to gravitation is that the block is also exerting a force of attraction. So that's the force by the block on Earth. Yeah, so I've shown it as dotted because it's a force that is being exerted on the Earth, while the earlier force, FEB, is shown with a solid line because that's a force which is experienced or which is exerted on the block. Yeah. So later on in the free body diagram, as you will see, we are interested only in the forces that are acting on the block. So with respect to the nature of the forces in the pair, the forces are opposite to each other and equal in magnitude. So FEB will be equal to negative of FBE. Yeah. So magnitude remains the same, but the direction of both the forces in the pair is opposite. So another important thing is any of the forces in the action-reaction pair can be considered as action, and the other force can be considered as reaction. It doesn't really matter. Yeah. So let's see now what is the action-reaction pair of forces. as far as normal forces are concerned. So we know that forces always come in pairs. So I have still not defined what's a normal force. We will talk about it a bit later. But given the nature of the force, we know that a force cannot exist in isolation. So if you have a normal force in one direction, there will be equal and opposite normal force in the other direction. So come back to our block system of block and then the ground. Yeah. And let's see what are the normal forces. So there will be, I can write this as Fn. That's the normal force by the ground on the block. So I could have also written this as Fn by the ground on the block. I don't want to complicate for the understanding purpose. So I will keep it as simple and I will call it as Fn. Yeah. And then in the action reaction pair, the other force will be F dash N. Yeah. F dash N. And what is that? That's a normal force by the block on the ground. So I could have as well alternatively written it as F dash of N, which is by the block on the ground. So by the nature of the forces in an action reaction pair, the Fn force will be equal in magnitude, but opposite in direction, represented by this negative sign of F dash N. Yeah. So that's very important. All right. So what I have done is I have put those pair of forces. So there is one pair of gravitational forces between these two objects, and then there is one pair of normal forces between these two objects. I have put them side by side to give a complete picture of the forces that are acting on the block. So you are aware of the concept of free body diagram. So if I have to draw the FBD of the forces acting on the block, then I should be considering only the forces which are acting on the block, and I should ignore the forces which are acting on the other object, which is earth or ground in our case. So let's see what are the forces which are acting on the block. Yeah. So the first force that is acting on the block, as you can see over here, that will be FEB, yeah, which is weight, which is equal to mg. And how about the second force? Is it a force acting on the block? No, it's acting on earth, so I can safely ignore this. So out of the two forces, I will consider only the first one. Now let's move to the other pair, normal force. So look for the forces which are acting on the block. So this is a force which is acting on the block, and therefore I need to consider this. And how about the other one? So F dash N, yeah, that's a force acting on the ground, so I can ignore it. So for the purpose of my free body diagram for the object which is block, I need to consider only Fn from the action reaction pair for normal forces, and I need to consider only FEB or the weight or mg of the block to make the free body diagram as a complete diagram. For the other forces, they are not relevant in the picture. Yes, they do exist, but they are not relevant as far as the free body diagram for the block is concerned. Yeah. So remember this point before I go to the next slide. So let's draw the free body diagram for the object under consideration, which is a block in our case. So free body diagram, as the name indicates. So when it is free, it means it is free from any net force. So whenever there is no net force acting on the object, and you try to represent all the forces acting on the object, that diagram will represent free body diagram. So from Newton's second law, for an object in equilibrium. Now, it's important also to define what is equilibrium. In our case, the object is at rest on the ground. So since the object is not doing any motion in any direction, so in our case, the forces are acting in the vertical direction. We will comment on the horizontal direction in few other videos, but in this case, we are focusing only on the forces acting in the vertical direction. And since we know that there is no movement of the object vertically, it's not moving up, it is not leaving the surface of the ground, and it is also not getting into the ground. It's just on the ground. Yeah. Therefore, since the object is at rest, the Newton's second law will apply like this. The net force on the object has to be zero, which is as good as saying sum total of all the forces that act on the object should be zero. So the forces coming from the previous slide, what are the forces which are acting on the object? There are only two forces. So first is the force by earth on the object, which is the weight of the object, which is given as mg. And the other force acting on the object in the vertical direction is Fn, That's the normal force by the ground on the block. Yeah. So these two forces added together should be 0. So in our case, there is no horizontal force acting on the system. And therefore, I can safely write it as F net in the y direction equals to 0, and sigma of all the forces in the y direction is equal to 0. So which means Fn represented by the vector plus the weight, these are the only two forces in the vertical direction, should be equal to 0. So which also means that Fn should be equal to negative of the vector weight. In terms of the magnitude of Fn should be equal to the magnitude of weight, which is given by mg. So this is the condition of equilibrium. Yeah. So let's now go into the conditions for the normal force to exist. The first and foremost condition is that the two surfaces should be in contact. So here we see that the block and the floor or the ground, they are in contact. But that's not the only condition. We should have another condition, the second condition that should be additionally satisfied. The two surfaces must press against each other. That's very important. That means they should apply a force against each other. So if we have only the first condition being met, it may not result into a normal force. Both 1 and 2, when they are met, then the normal force will come in the picture, as I will show more with the figures later. Now let's go into the reason for the existence of the normal force. So we are trying to understand more and more about the normal force. The normal force is a result of the interaction between the electrons of the two surfaces in contact. That's very important. So since we have the interaction at the level of the electrons, therefore normal force is a type of electromagnetic force. And you may already be aware that electromagnetic force is a fundamental force. There are 4 type of forces which are fundamental in nature. Which are they? There is a force due to gravity, yeah, and then there is also electromagnetic force, which is the force we are talking about when we say normal force. So that's the second type of force. And the third one is the strong nuclear force. We will not go into that right now, but you should remember there is a strong nuclear force, and there is also a weak nuclear force. So out of the 4 fundamental forces that exist in the nature, if you are asked to qualify under which of them the normal force will be represented, then your answer should be electromagnetic force. Now let's consider the question, when do we have the normal force applicable in the given scenario? So these are the scenarios. So in our case, we took the object at rest, but the free body diagram or any of the description that I mentioned before will not change if I would have mentioned that the object is in motion along the surface. Nothing changes. Yeah. So because normal force will be acting in the y direction, which is perpendicular to the surface, so it really doesn't matter if there is a net force along the x direction. So if the net force along the x direction is 0, then we say the object is at rest. And if there is a net force along the x direction, then the object will be considered to be in motion. From the perspective of the y direction, normal force being applicable only for normal to the surface or y direction, it really doesn't matter whether the object or the block is at rest or in motion along the surface. Another important point is, does it really matter if the surface is horizontal, which means no inclination, yeah, or if the surface is inclined at some angle theta to the horizontal? No, it really doesn't matter. The normal force will still be there, and the rule of the normal force will be that it is always perpendicular to the two surfaces in contact. Now, something more about defining the normal force. We did the description earlier. Now, time to recap. So, normal force follows the concept of action-reaction force pair, just like any other force in nature. As I mentioned, forces always occur in pairs. So any one of them can be considered as a action, and the other one in the pair will become the reaction. So important to mention that normal force exerted by block on the ground is equal in magnitude and opposite in direction to the normal force exerted by the ground on the block. Yeah. Being action and reaction from Newton's third law, to every action there is an equal and opposite reaction. So these two forces make action-reaction pair. Now, something about the direction of the normal force. Yeah. So we know that it is perpendicular to the surface, and since it is perpendicular, we call it as normal. Yeah. But to make it on a lighter note, there is nothing like abnormal force and normal force. Yeah. So the name has nothing to do with the opposite of abnormal. It is a normal force because it is perpendicular to the surface. Another important thing is that though the contact is along the surface, which is parallel to the surface, the normal force acts normal to the surface. Very important. So you can also take the point from here that normal force happens only when the two surfaces are in contact. Yeah. So it's a contact force. There are two type of forces. You may already be aware. There are field forces and there are contact forces. So field forces may not require the contact. Example of a field force is the gravitational force, whereas normal force, it will happen only when there is a contact. Yeah. And how we can say that the normal force is perpendicular because of the reason that I mentioned here. So we have the weight of the object which is acting downwards. So to counteract the weight, there has to be a equal and opposite force which should act in the upwards direction. And that is why we say that normal force has to be pointing upward always. Yeah. So the weight will act downward and the normal force will act upward. Yeah. How about the point of application of the normal force? So where do we consider the point of application for the weight? Yeah. It is at the center of the mass of the object. So without any exception, the normal force will also use the same concept. That means it will be applicable at the center of the mass of the object. And for that matter, talk about any force, all the forces are always assumed to be working or applicable at the center of mass of the object. And finally, here are a few questions that came into my mind that the students or learners may have this question when they study the topic of normal force. So first question, how can we imply that indeed there exists a normal force? So what's the reasoning? What would have happened if this normal force was not present? Yeah, then as you can understand, it would be only the force of gravitation, and then the object would actually move into or inside the ground. Yeah. So since that is not the case in all the practical problems or numericals that you will be having in your syllabus, it will always be that the object is not moving into the ground. So therefore, definitely there must be a force exerted by the ground on the object, which indeed we call it as normal force. Yeah. Next question. And what would happen if the normal force was not equal in magnitude to the force of gravitation? So although we know that normal force is always equal to the force of gravitation, but if Fn was bigger than the weight of the object, then the object will actually lift up. Yeah, we know practically it does not happen. That's because it is equal. But if Fn was not equal, if Fn was bigger than the weight of the object, then there is a net force in the y direction, and then the object will actually lift up. Yeah. And what happens, or what would have happened if the weight was bigger than the normal force? Yeah. Then there will be a net force in the negative y direction, and the object will sink into the ground. Yeah. So since that is not the case, Fn is never unequal to the weight. It's always equal and opposite to the weight, and therefore we have the equilibrium, and therefore we are able to say that normal force is equal to the weight of the object. And finally, can we calculate the normal force on the object? Very easily. So in some cases, like the case we discussed earlier, the block placed on the ground, it's a straightforward calculation wherein we see that applying the free body diagram concept, Fn will be equal to negative weight of the object, or in terms of magnitude, Fn will be equal to the weight of the object, which is equals to mass times gravity. But in some other cases, yeah, the normal force, it will not be a straightforward, you cannot estimate unless you arrive at that number doing the calculations by keeping in view the other forces that are acting on the object. Yeah. How you have to draw the free body diagram. The more enhanced, or I would say complex free body diagrams will also consider some other forces. For example, there could be forces due to friction at play. So you have to see and apply those forces in the free body diagram accordingly. And as a result of those calculations, you will arrive at a number for Fn, which is the normal force. Now, let's apply our understanding to the scenario given. We have two blocks of mass small m and capital M at rest on the ground. And since there is no motion along the x direction, we do not have any forces along the x direction. At the same time, in the y direction also, we do not have any motion, but we still have equal and opposite forces. So talking about the free body diagram for the bigger object, we will have force acting in the positive y direction will be the Fm, that is a normal force by the ground on m, while equal and opposite force will be the weight of the object given by mg. Use the same logic for the smaller m, where Fm will be the normal force by the ground on the smaller m, which will in turn be balanced by its own weight given by mg. So Fm will be equal and opposite of the weight. Okay. In terms of the magnitude, Fm will be equal to mg. And using the same logic on the right hand side for the bigger object, we will have Fm will be equal to negative weight. In terms of the magnitude, Fm will be equal to m times g. But what about, will there be any normal force along this surface which is common to both the objects? What do you say? So if you recollect, the conditions are for the normal force to be present, they should be in contact. So that first condition is met. Yeah. So they touch each other. Yeah. That condition is met. But is the second condition met? That is there any force being applied by the bigger object onto the smaller object? Or is there any force being applied by the smaller object onto the bigger object? In the scenario that is given, no, there are no such forces. Yeah. So if there is no such force, which means there is no external force acting on the bigger object, no push or pull happening along the x-axis, and there is also no push or pull happening for the smaller object. Due to that reason, there will be no normal force by a smaller object onto the bigger object in the x direction, and there will also be no normal force by the bigger object onto the smaller object in the x direction. The whole point is, since they are not pressing each other, they are not exerting force on each other, therefore there will be no normal force between them. Thank you for watching the video. In case you like the video, please press the like button, and also if possible, please subscribe the channel if you want to be notified for any new videos. Also, please share the video with someone who can benefit. It will be lovely to have your comments. Thank you.